Okay, welcome back, everybody. So today we're going to be talking about increasing and decreasing functions. And today's objective is to determine whether a function is increasing or where a function is increasing and where it's decreasing. Just a quick note before we start. If you wouldn't mind, please subscribe to the YouTube channel so that you can receive push notifications from me. Also, if you wouldn't mind, you could maybe hit the like button so that more people see math videos in the world. YouTube can push the videos to a larger audience. And that'll be beneficial for everybody. I mean, who doesn't want to learn math and specifically about increasing and decreasing functions? All right, okay. So there's my pitch, and now let's move on. Okay, so couple things. Today we're going to talk about the definitions of increasing and decreasing functions. Parts of it are quite simple and straightforward, and then other parts are quite complicated. And some parts of it are kind of beyond the scope of HL Math. I'll provide you with supplemental reading resources if you're interested, but some of the things today I am going to gloss over. Okay, first thing. So say you have a function here. By the way, you should pause the video here and just jot down everything on this page. There's quite a lot. But after you've done that, here's a function, and the function that we have kind of starts here, does something like this, comes down, it has a vertical asymptote here, and then continues on its way. Increasing and decreasing intervals, really they're just ways to describe where a function's y values are going. Are the y values increasing on a particular interval or decreasing? And so when we say a function is increasing on, we use the word on, what we're saying is give me the x values for which the function is increasing. Or when we say the function is decreasing on, we say, oh, give me the x values for which the function is decreasing. Now let's deal with the first case, increasing. A function is increasing if, as you increase the x values, so maybe you increase the x values from a to b, the y values also increase, okay? And then maybe you increase the x values beyond x equals d, then the y values are increasing. So a function is increasing, at least in our case, it seems to be increasing from a to b, and I've shown that in blue. And it's also increasing past d. I'll talk about the boundaries, the endpoints, in just a second, but for now that's the basic idea. Like as you increase the x values from a to b, the y values seem to be increasing, and then as you increase the x values beyond d, the y values are also increasing. Okay, and then the function is decreasing on, well, you can see that the function is decreasing from b to c. If we increase the x values from b to c, the y values seem to be dropping off. So the function seems to be, let me do this in purple, the function seems to be decreasing on the interval from b to c, and it also seems to continue to decrease from C onward down to D. So we'll say between C and D. Now, what you have to worry about next are the endpoint scenarios. And the endpoint scenarios are kind of difficult to capture, at least, based off of what the syllabus says and what you need to know as HL Math students. I'm just going to give you a general rule of thumb, and I'll try and justify why it's true. But it's harder to get into more detail until I give you a more precise definition. But here's the general rule of thumb. The general rule of thumb is include the endpoints if the function is continuous at the endpoints, and exclude the endpoints if the function is not continuous there. So what I mean by that is we would include x equals a. So let me do that here. Actually, we would include x equals a, and we would include x equals b, okay, because the function is continuous here. We would exclude x equals d because the function seems to have a vertical asymptote here, so it's not defined here. And then where it's decreasing, we're gonna, let me just do this in purple, we're gonna include b, include c, and then we're going to exclude d because the function is not defined there. Now, the reason we include the endpoints, okay, so let's first talk about maybe a. Why is it that we can include a as the function being increasing there? Because actually the derivative doesn't even exist there. How can the function be increasing there? How can the function increase on a point? And this is one of the other things, is the function doesn't increase on a point. It actually increases on an interval. So if you imagine like a range of x values from a to b, the y value at x equals a is the minimum y value on the interval from a to b. So the minimum y value is guaranteed to be smaller than any other y value in this interval. So we're okay, we're safe to include that. And for the same reason, we're safe to include x equals b, because if you just look at x values in the interval from a to b, the y value at x equals b happens to be the largest y value in that interval. And so, any other interval that you look at, or any other pairs of values you look at, the function will be increasing there. I know that it is a little bit of a hand-wavy argument. And the other thing is, maybe it's also confusing that you're including b here as well as here. And again, that's because you're looking at different intervals. So on the interval from b to c, the function continues to drop off. And like at x equals b, it reaches its maximum value. So it's okay to include it in both the increasing and decreasing interval. For a more precise argument about why this is, I'll link an article below that explains it really well. Okay, the definition though that we're going to take is the following definition. This is the one that's presented in your textbook. If s is an interval in the domain of the function f, then the following is true. If f of x is increasing on s, then it's only going to happen if the following is true. So f of x is increasing on s if the derivative is bigger than or equal to 0 for all x values in s. So graphically, I can show you this. So if you look at the interval from a to b, and we draw some tangents, remember the slopes of the tangents are what the derivative represents. The derivative represents the slopes of the tangents to the curve at some x value. You can see that the slopes of the tangents to the curve are always positive when the function is increasing, or perhaps 0 at the boundary condition x equals b. So this definition here is the definition that we'll use in MathHL for determining whether a function is increasing. Similarly, a function is decreasing on an interval s if the derivative is, maybe I shouldn't do this in this color, if the derivative is less than or equal to 0, for all x values in that interval. And you can just confirm that graphically, like if you draw some tangents to the curve in the interval from b to c, or from c onward to d, you'll see that the slopes of the tangents are negative or 0, and so the function is decreasing there. The other thing I forgot to mention is you can actually combine these two intervals, and actually in calculus you might see this where the interval is given in interval notation. So you might write this as x belongs to the set of real numbers starting from b and going all the way up until d, but not including d. Okay, because here we have x values bigger than or equal to b, less than or equal to c, and bigger than or equal to c, less than d. So we can kind of combine these two intervals together. Okay, so that's the basics of increasing and decreasing functions. Again, the boundary conditions, if the endpoint is continuous, if the function is continuous at the endpoint, include it. If the function is not continuous at the endpoints, exclude it. And I think that's the easiest way to go about answering whether to include or exclude the endpoints. More thorough discussion on that is, I'll provide a link to that down below.